Morning guys. Okay, last lecture we have solved the numericals on optimum design. Those numerical asked in the SPPU last year question paper. Today also we'll see the some numericals asked in the SPPU examination. Okay, see the statement of the problem. A shaft is required to transmit. Here is a 900 Newton meter torque and torsional stiffness 90 Newton meter per degree. Required factor of safety is 1.5. FOS value is given 1.5. Design the shaft using maximum shear stress theory. Which theory we want to use here? Maximum shear stress theory for minimizing the weight of the material. Our aim is minimizing the weight of the material. The property are as follows. Some property of the material as given. There are three materials are given in the first column: alloy steel, aluminum, magnesium. That three materials are given. Related that material, you have given density of that material, then tensile strength of the material, and modulus of rigidity is given. Okay, this value we will see for the alloy steel 7800 kg per meter cube density is given. Then say tensile strength is given 450 MPa, or we can say the Newton per mm square, and modulus of rigidity, this is denoted by the G. Okay, modulus of rigidity is denoted by the G. It is given 82 into 10 raised to 3 for the alloy steel. Similar way, these values are given for the aluminum and magnesium. Okay, then see, this is the given data. With the help of the given data, we want to find the or we want to do the minimizing the weight of the material. Okay, we'll see the details. First step, we'll see the stepwise. Identify the all the dimension. Dimension we'll find, but before going on the dimension, identify the all design parameters. Okay, W is the weight of the shaft in Newton. Okay, what is the given and what is the meaning of that notation? You know that. Okay, rho is the mass of the density of the shaft. This is given in kg per meter cube. D is the diameter of the shaft in meter. L is the length of the shaft in meter. T is the torque transmitted by the shaft. This is given Newton meter. K is the torsional stiffness of the shaft, Newton meter radian. This is given in degree, but you should convert into the radian. Kt is the combined shock and fatigue factor. Okay, FOS is the factor of safety, or it is also denoted by the NF. Okay, tau max, maximum induced shear stress in Newton per meter square. This is given Newton per mm square. You should convert into the Newton meter per meter square to Newton per meter square. SSY, SYT yield strength of the shaft of the material. This is given also in Newton per meter square. SSY yield strength in a shear material. Okay, this is also given in Newton per meter square, and G is the modulus of rigidity is of the shaft. This is the Newton per meter square. Second step, to minimize our aim. What is our aim? To minimize the weight by deciding the optimum design. Okay, write the PDE primary design equation. W is equal to rho is given, G into A into L. Area is pi by 4 into D square. Okay, then next step, write the SDE equation, secondary design equation, based on the torsional stiffness. Okay, you know the K is equal to G into J into divided by L. We know that the polar moment of inertia J is equal to pi by 32 to d raised to 4. Okay, you should put that value and you will get the new relation K is equal to pi into G into d raised to 4 divided by 32 L. Based on the shear stress again, you will get the based on the torsional stiffness and based on the shear stress. Tau max is equal to Kt into T divided by pi divided by 16 into d raised to cube. Okay, you will get that relation. Then next is a step, write the limiting equation LE. Okay, tau max is less than or equal to SSY divided by factor of safety. Okay, or you can write limiting equation means this is given less than or equal to or equal to or greater than, means there are some conditions, you have given some limitations. Okay, this once you have written primary equation, secondary equation and limiting equation, then easily you should decide the parameters. Okay, parameters, this is the first parameter P. Yesterday we have seen that lecture. Okay, T factor of safety and K. Okay, torsional, this is the specified parameter, limited parameter and U oblique U parameter, mean unspecific and unlimited parameter. You should write all the parameter, which is the desirable parameter, which is the material property, which is the GP parameter. Okay, you should write all the parameter under the specified, limited or unspecified or unlimited property. Then combine the SDE with PDE. Okay, how to combine, you know that W is equal to, we already find rho g pi by 4 d square into L. Okay, and W is equal to rho g into pi by 4 d square. What is the value of L? L is equal to, we can write pi into G into d raised to 4 divided by 32K. Because of in the fourth step we have calculate K is equal to, okay, then you can convert L is equal to pi G d raised to 4 divided by 32K. This is the equation number 1. Okay, then again you can solve this equation, then you will get the new equation pi G small g into capital G pi square divided by 120K. Okay, this is the you will get the new equation. Then final equation, you will get the W is equal to 2 rho g kt square t square divided by K into tau max square. Okay, next step, W is equal to 2 rho g kt square t square divided by into, put the value of tau max 0.5 SYT divided by factor of safety square. If you are putting the all the values, okay, you should choose the kt is equal to 1. Okay, before going on that, you should choose the minimum value. Check that how to calculate that minimum value. In the given table, rho is given, SYT is given, G is given, then rho into G into divided by SYT square. This is the constant, okay, or factor. You should check the which value will get the minimum. 3.15 1585 into 10 raised to minus 3, 3.36 into 10 raised to minus 3, 3.06 into 10 raised to minus 3. Third material having the less value, we will choose that value, magnesium. Okay, select the Mg material as lowest value, Kt is equal to 1. We are assume that. Last step, eliminating the geometrical parameter, tau max is equal to 16 ktt divided by pi d cube. Already we have calculated. Put the all value and calculate the d and L value. D is equal to, you will get the 51.615. Then K is equal to, we know that pi G d raised to 4 divided by 32 L. Step number 4. K is in Newton meter degree. We want to convert into the Newton meter per radian. Then multiply by 180 by pi. Okay. Then you get L is equal to 2.2971 meter. And finally, we want to put the value of rho g SYT square. Okay, all the value. Then you will get the weight. we want to minimize the weight. W is equal to, if you are putting all the value in that equation, you will get the W is equal to 84.8755 Newton. Guys, also I will give the for homework, you try to solve this numerical. What is given in that numerical? See, design tensile bar of length of 200 mm. L is given 200 mm. To carry the tensile load of 5 kilonewton, F is given 5 kilonewton. You should convert into the Newton. 5 into 10 raised to 3 Newton for minimum cost out of the following material. Here we want to write the cost formula each and every. In the step C, identify the given element. Okay, which elements are given. Factor of safety is not given. You should assume the factor of safety 1. Okay, write the PDE equation, write the secondary equation, write the limiting equation. Once you have write that equation, then make the parameter table. Okay, for each and every material. Okay, design parameter based on the study of the status of that design. Find out the different parameters: specified, limited, and unspecified and unlimited. Then you should write the combine SDE with combine PDE, combine SDE with PDE. Okay, again combine PDE with limiting equation. Then after that you should choose the limiting value of that factor. Okay, again you should write the table and find out the constant rho into C divided by SYT. Okay, then after that calculate the value of eliminating geometrical parameter, means you should get the value D, and you will get the one relation CM is equal to, use that relation and find out the minimum value. Okay, today we'll stop here.